Okay, so I'll start the session. Do you have any questions to ask? Have you watched the lectures? Okay, so do you have any specific questions? Yeah, go ahead. Yeah, it's okay. You can ask. Mhm. Okay, what do you mean by initial velocity and steady flow velocity? Mhm. Okay. Oh, so you mean by initial velocity, you mean the starting velocity? Oh, okay. No, it is the steady flow velocity because, see, there are. So for that, actually, there are different techniques like variable throat nozzle, or you have a secondary throat. Yeah, so those are the things. Okay, so did you get any notification that you will have a TA session or something on WhatsApp? Okay. So how many students are actually registered for this course? My God. Okay, I don't see that many people here. Anyway, so I think I'll just start. So the aim of these sessions is that I will be discussing some very basic concepts which are covered in the corresponding week's lecture, and I will also solve some questions. So these notes and questions will be designed by me, but they'll be almost in sync with the weekly lectures that you will watch. But the best thing about these lectures would be that you watch what the professor has already shared, and then if you have any doubts from that, you come and ask me during these live sessions. Okay. So that said, I'm according to me, what has been discussed up till now is just the basics of thermodynamics and basics of fluid flow, right? Okay. So we'll start with very simple things, and it will be great if you can answer, Yash as well as Deependra. Okay, so can you tell me what is yeah, hi. So can you tell me what is a compressible flow? I'll also present my screen. Okay. Okay. So first, okay, maybe I should have asked this. What is a flow? What is a fluid? What do you mean by flow? Yeah. Okay. So just give me a minute. I think something's gone wrong with my writing tab. You're able to see what I'm writing, right? Yeah, something's gone bad. Just a second. Okay, so no, that is not a satisfactory answer. What is a flow? Mm-hmm. Yes. Yes. So the answer is that there has to be relative motion between the layers of the material when a shear force has been applied. Okay, so that is what a flow means. So I'll just, okay, I don't know what is the issue with the writing. tab. Anyways, and compressible, like you said, it is a significant density change in fluid, in the control volume of a fluid when some pressure is applied, and that will lead to changes in the density and the temperature, right? So do you know what is the definition of compressibility? Definition of it is a modulus for a substance. What is modulus? I don't know. Okay, I don't know what is Young's modulus. How do you define compressibility? So you said there is compressible means what? That there has to be change in the density or change in the volume when pressure is applied, isn't it? Yeah, so okay, I am not able to write. I'm so sorry about this. It's writing now. Lag in my speaking or in my writing? No, I think it's just that my writing tab has stopped working suddenly. It was working perfectly fine a few minutes back. Okay. Okay, so when I try to write the formula, I'm not able to write it. Okay, anyways, you can please, yeah. Okay. That's okay. I think I'll fix this next time. But yeah, but maybe then I'll have to orally tell you the formula. Okay. Okay, so you go ahead and tell me the formula then. Compressibility formula. So maybe I can try and write it in the text. So what is compressibility? It has to be a fractional change, the ability to be compressed. Okay, no, so compressibility is when I apply some pressure, okay, and there is a change in the volume, isn't it? So compressibility is defined as the fractional change in volume when a unit pressure is applied. So what is fractional change in volume? Delta V divided by the total volume V, right? And that per unit pressure. So delta V by V, the whole divided by delta P. But then we know that if I apply pressure, the volume is going to decrease, isn't it? So delta V is going to be a negative quantity. So we just put a minus sign in front of this. So compressibility is minus 1 by V into dV by dP. Is that clear? So I just hope at least you can write it down in your own notebooks, and maybe after the class I'll make the notes and you can see it on the link. Okay, so now what is a perfect gas? Oh, can you give me an equation of state? A simple equation of state? Okay. PV is equal to RT, right? And another way to write this would be P is equal to rho RT, right? Okay, so I'll write rho as rho actually. Alright. Okay, that's fine. So do you know the value of R? Must be knowing in SI units. Oh yeah, 287 So I'm just trying to brush you through very simple things which you already know, so that when we solve the questions, this will come handy. Okay. And yeah, one of you mentioned that perfect gas is something in which the internal energy is not dependent on. It's not dependent on temperature. Only dependent on temperature. But what are the other possibilities? In a real gas, internal energy would be also dependent on density, volume. Yeah. Okay. So before we say that internal energy is actually dependent on temperature, what is internal energy of a gas? Right. So internal energy is due to motion of the gas particles. I'll write that in short. Motion of gas particles, right? Okay. And then we said that energy is just a function of temperature if we have a perfect gas. Then can you tell what is enthalpy? Total energy. So we have already talked about internal energy. So what is total energy? Flowing. Flow. What do you mean by that? Right. Yeah, so we can either call it flow energy or we can call it pressure energy, right? So enthalpy, which we'll denote with H, is actually equal to the internal energy plus PV. Okay. Yeah. So you said H is E plus PdV. That's not right. H is E plus PV. Okay. Yeah. So what is PdV actually? Since you have already mentioned. Work. What work? Work done by whom? It can also be work done by the fluid, right? It can be work done by the fluid or work done on the fluid. So PdV is equal to, so I'll write it as dW. Okay, so can you tell me the difference between state variables and path variables? Difference between state variables and path variables. State variable would not depend on the path. That's what you're saying. Yeah, it will depend on the initial and the final state. Right. Okay. Yeah, I'm sorry. I don't understand this complete integral. So could you give an example? Yeah. Okay. Yeah, it's started working somehow. Okay. So if I consider this graph between P and V, pressure and volume, so between any two states, I can take any path, right? But the final temperature, so the temperature at this point and the temperature at this point, that change in the temperature is not going to depend on what path I took, right? Yeah, so that is a state variable. But how much work has been done in either case, that will depend on what path I took. So that is a path variable. Okay. Yeah, so you got it right. Okay, so you know what is Cp, Cv, gamma, these specific heat constants? Okay. So can you tell the definition? Cp, Cv and Yeah, Cp and Cv basically. Okay, it's good that you're answering, but can someone else also answer? I'm hearing the same voice. I want everyone to be involved. Yeah, so he's already told the answer, right? You told the answer for Cp. Volume is constant for Cv, and what do we get? What is it? How do I define it? Yeah, but at constant pressure, what is changing? Heat is supplied to the system. Okay, so now if I go back to my equations, the basic equations, and I keep pressure constant, so if I take this H is equal to E plus PV, so in the differential form you can write it as dH is equal to dE plus PdV plus VdP, right? So now if I keep constant pressure, this term is 0, isn't it? So Cp is defined in terms of dH by dt at constant pressure, whereas Cv is defined as dE by dt at constant volume. I hope you know this. Yeah. Okay, and then what is the relation between Cp, Cv and R for perfect gas? Right. Okay. So I think I should just quickly write down the formulas that we need. So Cp is equal to, I'm sure you know this, gamma R by gamma minus 1, and Cv is equal to R by gamma minus 1, and Cp by Cv is equal to gamma, right? Okay, so let us do one thing. Let us solve some questions. We are going to calculate the isothermal compressibility for air at a pressure of 0.5 atm. So I'll give you just 2 minutes. You can solve and tell me the answer. We have already discussed the formula. Okay, now that my pen is working, let me write the formula of compressibility. I'll go up and write it. Okay, so what you are given is the pressure of air, and for air, if you need any information like gamma or R you know, gamma is 1.4 for air, so you can just solve this. How will you go ahead? How will you proceed? Anyone has any idea? Theta equals to 1 upon P. Okay. So you know the formula from somewhere, or you have derived it. Do you know how to derive this formula that you just told me? Okay, so please help me out. So let me write, so you called it beta, so I'll write it beta. Beta is, like we wrote earlier, minus 1 by V, dV by dP, and this is at constant temperature, isn't it? Okay. Okay, so we will use the ideal gas equation. PV is equal to RT, and then so yeah, so V is RT by P, and then we can find dV by dP, which is minus RT by P square. So if I put this into that equation, what do I get? Beta is equal to 1 by P. So yeah, you'll get the answer as 1.98 into 10 to the power minus 5. So I request you, even though these questions are pretty simple, just be in a habit to have a calculator and immediately do the calculations, because that will help you for your assignments in the course as well. Okay. Okay, so we'll move on to the next question. If anyone has doubt, you can ask me now. Okay, so the next question is about a pressure vessel that has a volume of 10 meter cube. Okay, so let me keep writing what is given. So the volume is given to be 10 meter cube. The pressure is given to be 20 atm. Temperature is given to be 300 Kelvin. And the question is pretty straightforward. You have to calculate the mass. So what will we use? So we know rho is equal to P by RT, right? Am I audible? Yeah. So please keep engaging. Otherwise, I think I've lost my connection or something. Okay, so you can just plug in the values and get density. So can you tell me the answer now? I'll wait. And then mass is simply density into volume, right? I'm not going to proceed unless you give me the answer. Please give me an answer. You know the value of R? We just wrote it down. Is anyone calculating? Guys, is anyone doing the calculation? Yeah. Anyone else except Yash? So you have to convert atmosphere into Pascal, right? So you'll say 20 into 1.01 into 10 to the power 5 Pascal. So what is density? What is mass? Yash, by now you should have got the answer. Yes, it's 23.46 kg per meter cube, right? Yeah, so obviously the mass is just 10 times this, so that's 234.6 kgs. Okay, so with the same pressure vessel, now we'll calculate the total internal energy of the gas. So how do we calculate total internal energy? What is E? CV into T, right? So and what was CV? We just wrote the formula in terms of R and R upon gamma minus 1. And gamma we'll take as 1.4 for air. So can you please calculate internal energy? Right, so what is important here is that we have been asked the total internal energy, and the formula that is written here, this is what? This is specific energy. So this is specific internal energy, right? So we need to, yes. Yes. Yeah, so it's per unit mass. So for example, if I have to, yeah, so the example that you gave, so your question is, why are we using specific quantities? Why don't we just compare the total quantities? So if I have to compare the specific fuel consumption of two aircrafts, but both these aircrafts are designed for different missions and their weights, their payloads are different, then they are not going to be same. But their design has to be still compared, which one is more efficient. So how much fuel am I giving per unit mass of intake air? Yeah, it acts for a reference to compare. Does that make sense? Without the constraint of size, we can compare two engines, right? Yeah, with the specific quantities. Yeah, you cannot say that, see, one aircraft is using only 10 tons of fuel and the other is using only the other is using 20 tons, so the one which is using 10 tons is more efficient. That's not true. It is traveling a lesser distance, it has lesser weight, and still it is using 10 tons. You're getting it, right? So the total, yeah, the total quantity won't help. Okay, so the answer given here by you is 717.5 joule per kg Kelvin. Okay. Is that what you have given the answer? Because that's not what I have here. Right. Okay. So let me do this. So then what is the total energy? Mass, we just calculated 234.6 kg. How much? Yeah, so if you give me an order of magnitude, it would be like 5 into 10 to the power. Okay, 5.05 into 10 to the power. Yeah, that's fine. So why are you shocked with the magnitude? Right. So this is precisely why the total quantities don't make sense sometimes, because you're dealing with air and you can't even imagine that air has so much internal energy, right? Okay, so let's have some more basic concepts now. What is the zeroth law of thermodynamics? Zeroth law of thermodynamics. Anyone? Anyone other than Yash? Yeah, please speak up. We should make most of this time. Yeah. The equilibrium concept. Okay. So if I say A has the same temperature as B and B has the same temperature as C, then A and C also have the same temperature, right? Thermal equilibrium, right? Only thermal, that is how it was proposed, because we are assuming A, B and C are like, they are not exchanging masses, right? So but if you allow mass exchange and then you see the composition, then you have to check whether the chemical composition is same, are they going to react. So no, chemical equilibrium is not going to come from here, only thermal equilibrium. Okay. Okay, so now what is the first law of thermodynamics? And I don't want the Kelvin Planck statement from the textbook, I want the essence of the first law. Okay, so do you know how first law was proposed? Was it from some theory? Was it derived from some governing equations like Navier-Stokes equations? Yeah, but I'm asking, was it analytically derived from continuity equation or momentum equation or something? Like, see, in fluids you have Navier-Stokes equations and everything comes from that. So I'm asking, in thermodynamics, this is the most fundamental law. Do you think? Energy balance. So no, this was not derived anywhere. This is an empirical law. Okay. So what does empirical law mean? That it has been proposed like an axiom and practically observed, right? Okay, so what is the first law of thermodynamics? So let us consider a system, some system A, and it has a surrounding, right? So this first law can be written in simple way, that delta Q plus delta W is equal to dE. Okay, before I even explain this, I want you to mark how I have written Q and W with a delta. This is infinitesimal change, and internal energy I have written with D. So do you know what that means? No, they are integrable. Why are they not integrable? No, if we know the path, we can integrate them, right? So that's the whole thing. They are path variables. No, there's nothing about reversible, irreversible here. The reason why I've written Q and W with deltas, because they are path variables. So when you integrate these quantities, you need to know the path of the process. But dE, there you just need to know the initial and final state of the system, right? Does that make sense? Yeah. Okay, so now the question, so what is first law? It states that if I have a system, its internal energy will change. So internal energy will increase if some work is done on the system or if some heat is added to the system. So these are the only two ways by which the internal energy can change. On the other hand, if the system does work, then its internal energy will decrease, and if it loses some heat because of friction, or if it is a source, so it is going to dissipate some heat, then again its internal energy is going to decrease. Okay, so I'll just write some equations which again you must be aware of from 12th standard science, or maybe from the lectures. So I'll just quickly write all this. We know delta W is what? Delta W is P dV, and we also know dH, right? So dH is equal to dE plus P dV plus VdP, right? So I can use all these equations and rewrite the first law like this: dH is equal to dE plus delta Q. Okay, now what is second law of thermodynamics? A complete transfer of heat to work is not possible if we, okay, so if we have only source and we don't have a sink, no, but such a system can exist. Yeah, that is right. But is it possible to have only a source and not a sink? In reality, practically, it is not possible. Yeah. So earlier you mentioned something like a reversible and irreversible process. So can you tell me what is reversible process? Small steps, I think you mean quasi static, but see, that is how we explain that practically reversible process can happen quasi statically if you change in small steps and then you can revert back. But what reversible process essentially means is that the system and the surrounding both can be restored to the original state exactly. If that is possible, then that process is called reversible process. Okay, so that is possible when there is no dissipation, there is no viscosity, thermal losses, or any mass expansion. Like if there is a chemical reaction and the mass changes, the density changes, then all that may not be reversible, right? Yeah. So okay, so now we know what is reversible. So I'll just write no dissipation, no dissipation of energy. Okay. So the next question is, what is adiabatic? What is an adiabatic process? No heat transfer, so I can just say delta Q is 0. What is an isentropic process? Adiabatic and reversible. So isentropic has to be reversible plus adiabatic. Okay. Okay, so let's get back to what is the second law. So second law says that, yes, yeah, so but we don't even know what is entropy right now. We haven't defined what is entropy. So yeah, go ahead and tell me what is entropy. I cannot define an entropy for adiabatic process. Okay, that is how an isentropic process would be defined. Yeah. So let me first define entropy. So entropy is defined as disorderness, degree of disorderness, and it is also, you can write it mathematically like this, delta Q by T. So what I want you to note is that I have not written delta Q reversible or irreversible and so on. But if it is an isolated system and the process is reversible and there is no heat exchange, then that process would be isentropic and the entropy would be 0. So did I clear your doubt? Okay, so in an infinitesimal form we can write delta Q is actually equal to T ds. So S is what? S is a state variable or a path variable? State variable. Okay, so now we already had some equations over here about delta Q from the first law and also from enthalpy equation. So I'll just write some equations which are very easy to derive. So TdS is equal to dE plus PdV. I hope you are aware of these equations. Okay, so TdS is also equal to dH minus VdP. Okay, so now we need to solve a question about the entropy, and we considered this pressure vessel earlier in question 2 and 3. So it's the same pressure vessel, but I've just written down the quantities that we already know. So we are given the pressure, volume, temperature, and we found the mass, density, CV. All these values we have found in the previous questions. So let us now do one thing. Let us heat the gas in this vessel And let us say that from 300 Kelvin we take this vessel to 600 Kelvin, right? So you have to calculate the change in entropy of the air inside this vessel. So how do we do that? Okay, what formula? Okay, do you know how to derive this formula that you are saying? It's very simple. So you take these equations itself, right? Yeah. So I'll just mention it. I'm sure you know this. So ds can now be written as dh by t, but dh was what? It was cp dt, right? So cp dt by t minus v dp by t, and you can use p is equal to pv is equal to rt over here. So you have v by t, that would be r by p. So if you just put this and integrate, you will get delta s is equal to cp log t2 by t1 minus okay, so we don't have any m over here, we don't have a mass because we are calculating right now the specific quantities. But of course you can multiply to, okay, let me write it as small s so that it is specific entropy. Okay, r log p2 by p1. And in the question we are asked the change in entropy of the entire air, so you'll have to multiply with mass eventually if you use that formula. Okay, so please go ahead and do the calculation and tell me the answer. So we can say that T2 is 600 Kelvin, right? I hope all of you are calculating. Okay, so other than this equation, we also have another equation in terms of CV and volume, right? So I'll write that also. Delta S is equal to CV log T2 by T1 plus R log V2 by V1. So which one of these forms will you use given all the information? Okay, please answer me. Is anyone calculating? Is anyone doing the calculations here? Yeah, okay. So which one are you using? The first one or the second one? Yeah. Yes. Okay. Yeah, you can find the pressure ratios because you have the temperature ratios. Yeah. Okay. No, but so what you said is that the volume is same because the yeah, it is a vessel. Hmm. Yeah, V2 will be V1, but the density will change, right? So I think it would be safer to use this P2 by P1 because that you can easily find as the ratio of, yeah. So you can find P2 by P1, right? It's T2 by T1. Okay, you're right actually. So it doesn't matter which one we use, and P2 should be equal to V1. Yeah, and then you can also say Cp is equal to Cv plus R. Which you will get here as 1004.5. So what is the specific entropy? Or you can also directly tell me the total entropy. Should I show the steps in more detail? Or is it straightforward? This you're telling me the total entropy? This is 1 point. You're close to it. It's 1.2 according to me. 1.2 into 10 to the power 5. Yeah. Anyone else? Yeah, sure. The value of T21. Yeah. So that makes this ratio 2. Okay. And what did you get as specific entropy change? So is only one person doing the calculation? Can others please speak up? Am I audible to everyone or only to one person in the meeting? No. Okay, that's how you found it. Okay, so this is 497.3 to be precise, and this is 1.16 to be precise. Yeah. Okay. Okay, so now I'll move on to different types of processes. So we have already discussed adiabatic and isentropic, and you must be aware of isobaric and isochoric processes also, right? So can you tell me on this diagram, in the PV diagram, which one is an isobaric process? The horizontal line. So this is isobaric. And what does the vertical line represent? Isochoric, right? Okay. Now there are two other lines. Which one of them would be isothermal? And which one would be isentropic? The lower one is iso. Okay, so the one I am writing is this one. This is which one? Are you sure? Okay, why? So if I represent a process like this, PV to the power n is constant, Then N is what for an isobaric process? P is constant, right? So N has to be 0, isn't it? Yeah, so this is N equal to 0. And what is it for an isochoric process? So for an isochoric, it will be N equal to infinity. So for an isothermal, if temperature is constant, what will be the value of N? 1, isn't it? Because PV is equal to RT and that is constant. Okay, and what is it for an isentropic system process? So do you know how to derive this? N is equal to what? Gamma. Do you know how to derive this? PV power gamma is constant. Okay, so like we said, isentropic process is when delta S is 0, right? Yeah, and we also had this formula that Cp log T2 by T1 minus R log P2 by P1 is 0. So you can easily rearrange all this and get P2 by P1 is equal to T2 by T1 whole raised to the power Cp by R, which is nothing but, so we know the formula of Cp is R gamma by gamma minus 1. So this is gamma by gamma minus. Yeah, so from there you can get the relation that P T to the power of gamma by gamma minus 1. So minus gamma by gamma minus 1 is constant, right? And then again apply P is equal to rho RT or PV is equal to RT, and then you get PV to the power gamma is constant. Okay, so this is, we started with delta S is 0, isn't it? So we got N is equal to gamma, and gamma is more than 1 for air, for example. Is it only for air or for any gas? Gamma is? For air it is 1.4, but in general is gamma? Yeah, so gamma has to be more than 1, isn't it? Gamma is equal to 1 plus 2 by F, and F is a number of degree of freedom. So anyways it is 1 plus something. So gamma has to be more than 1. Okay, so now if I look at these two graphs and let me consider just a small change in volume. So this has lesser decrease, steeper decrease, and this has lesser decrease in pressure, right? So which one is isothermal and which one is isentropic now? Okay, you do understand that if PV is constant and if I plot it on P versus V, so this is nothing but a hyperbola, right? Yeah, that is why we have the curve like this. Yeah, so which is isothermal and which is isentropic? So this one is? Okay, this is N equals to what and this is N equal to what? Okay, this is simple, isn't it? Yeah, so just say it. No, you're not saying anything. Oh, okay, so then I don't understand which graph you are referring to. Okay. Yeah, so this would be isentropic, right, and this would be isothermal. Okay, so now we have to do the same thing for the TS diagram. Now here, which are the easiest processes to name? What is the horizontal line? Yeah, isothermal. So this is n equal to 1. Okay, and what is the vertical line? Isentropic. So I'll just write n is equal to gamma. So now I have other two lines which are isobaric and isochoric. So first of all, why should it be like this? So let us consider this formula that we have. Again, delta S is equal to Cp. Yeah, so delta S is equal to Cp log T2 by T1 minus R log P2 by P1, right? But if the pressure is constant, then this term becomes 0, right? So I can just remove this term and I can say that delta S is Cp log T2 by T1 for isobaric. And similarly, we had another formula which was delta S is equal to Cv log T2 by T1 plus R log V2 by V1, but for isochoric that term becomes 0. Is that clear? Yeah, so for isobaric and isochoric we have this. So if I have the same amount of, first of all let us see, if the temperature increases, the entropy is going to increase, right? So that is why on my TS diagram, if temperature is increasing, entropy should be increasing. That is why the curve has to be like this, increasing, right? Is that clear? Yeah. So now you have to tell me, out of these two curves, so let me call them something specific. So this is curve A and curve B. Which one belongs to isochoric and which one belongs to isobaric? I have named them A and B. Okay, so you are saying B is isochoric, which is n is equal to infinity, and this is n is equal to 0. So how do we explain this? It's very simple. You just draw two lines. Let's say I am considering the same amount of temperature change here, right? So if you just see how much entropy change has happened on curve B and compare it to the amount of entropy change on curve A, you find that the entropy changed much more for curve A, isn't it? And that is what we expect because Cp is more than Cv. Anyone has any doubts? Okay, any doubts on this part? Okay, no doubts. Okay, so now I'll take questions which you specifically have. Anything from the lecture or any problem statement, you can actually go ahead and share your screen and show me the problem and we can try to solve it. Any questions? I request you to, yeah. Okay, you can ask the question. If I'm not able to answer, I will come back to you in the next session. Yeah. Okay, so you have a CD nozzle. Let me just maybe understand where you're facing the problem instead of looking at the problem itself. So you're saying that the shock is standing somewhere over here. Okay, and you are supposed to find the exit Mach and exit pressure. And what do you have as the input? Okay. So you've already started solving these questions? Okay. Okay, you're appearing for gate. Okay, why don't you tell me the values? Okay, so okay, why don't you tell me how you are approaching this problem and where you are facing the issue? Hmm. Okay, so are you given areas? So let me call this AS, AE, and throat area? Yeah, okay. Yeah, so you have the area MAC relation, and you also have the relation. See, what you would have is you have the throat area, and you have the exit area, and the shock, the area at which the shock is standing, isn't it? So you can relate the properties just prior to the shock in this region and after the shock. Yeah, so you can relate that. And then you will get the MAC number over here. Let me call it M1 and let me call it M2. You can do that, right? So now you know M2, you know AS, you know AE. You have to find ME from the area MAC relation. But so you know, yeah, so I'm saying that ME is completely a function of M2, M1, AS and AE, isn't it? So you know all the quantities. You know all these quantities, you have to find ME. So it won't be a function of M1, it's just M2, AS and AE. But is that how you solve area MAC relation? Is that what you use, by the way? Okay, but do you use gas tables? Oh, okay. Okay, then you have to work with the area MAC relation. Otherwise, you can easily use the gas table and go to the isentropic tables. And once you know M2, after this you assume that it is isentropic and then find ME, right? Yeah. Okay. Yeah. Any other question? Maybe you can tell me the integral equations. Are you referring to the integral form of the Navier-Stokes equation? Yeah. That is Navier-Stokes. So what is Navier-Stokes equation, by the way? Okay. Okay, so fluid mechanics, the basic governing equations, that is your continuity, right? What is your continuity equation? Can you help me? Oh, really? This is what is given in the lecture? So, I'm asking the equation. I'm asking the continuity equation. d rho by dt. Okay, let me see if you know this. Dou rho by dou t plus del dot of rho v. Okay, why am I not sure? Yeah, this is equal to 0. Yeah, you know this, right? And then you can rewrite this as d rho by dt plus rho del dot v, isn't it? You know this? Yeah, so now your question is, why do we have an integral form? Acha, so okay, so if you have a flow in a pipe, okay, let us consider a flow in a pipe, and again it stopped working. So, anyways, so if you have a flow in a pipe, you can calculate. Let us say you are given the pressure gradient across the pipe, right? Then how do you calculate the density change? How do you calculate the fluid properties? You are given the inlet density, inlet temperature, and let us assume there are no temperature changes, but you are given inlet density. You will integrate, right? Yeah, so am I not understanding your question? Hmm. Yeah, 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 that is there, but see, you should be able to go from the differential equation to the integral equations easily. So if you don't remember the integral equation, that is absolutely fine. You should remember the differential equation, and from there you should be able to go to the integral equation. Any particular concept which you want me to explain in detail in the next session, you can tell me that also. Yeah. Okay, sure. I can give you tougher questions. That is not a problem. But the syllabus needs to advance to a tougher level. Yeah. So I gave you the kind of questions which you will actually see in the assignment. Yeah. Okay. Yeah. Good evening. I'm not sure what do you mean by time, time and velocity displacement graphs. Okay. So yeah. Right. Right. Okay. Okay. So the piston is moving. You're saying that. Can you repeat? Graph of pressure versus displacement of this. Yeah. Oh, okay. Yeah. Okay. I understood. Um, you want me to just invert this, right? Oh. Okay. So this is the system. The piston is moving in this direction, and there's no boundary here. It's infinite. Yeah. Mm-hmm. Yeah. So what is it that you do not understand? How the pressure versus x graph would look? Time versus x. So how are you actually moving the piston? You're moving it with constant speed or something? It would depend on that, right? No, see, a time versus x graph would be if you're not having any external force moving the piston. Okay. Yeah, so so if you move this, for example, with some speed v, so all the particles are going to be pushed and a compression wave would be generated, and that compression wave would travel at a speed, let's say, I don't know, c. Okay. Yeah, yeah, exactly. That was that's what I was wondering. Okay. Okay. So, can you tell me how p versus x graph looks? Maybe I'm not still understanding what is this x. X is the distance between them. Hmm. Okay. So if I freeze it in time, then this is going to be like there is going to be a slight rise in the pressure where the wave is there, right? Yeah, between these two. But the motion of the piston is going to generate continuous pulses, so I would expect something like this. And if it is not going to decay, then uh, yeah, then the amplitude would remain same, isn't it? Okay, so you just suddenly move it and let it go at speed v, and then it is not giving any impulse. That is the problem. Huh. Yeah, so here it will be p plus dp. Okay, so it's going to be like this, and here is your wave, and here is your piston. Okay, so now can you explain what is this t versus x graph? Will be a hmm? Okay, so one he has drawn for the piston, and the other one he has drawn for the wave. So this one you're not understanding. Yeah. Okay, so what you're not understanding is why we have these two slopes, or which one would be greater. Okay. Okay, so how about I look into it and get back to you in the next session about this? Yeah, okay. Yeah, no, no, it's okay. Your name is? Okay, okay, I'll remember that. Okay, so I will explain stationary gas and moving gas analysis completely. Yeah. Anything else? Any basic questions that you don't understand? Navier-Stokes equation or thermodynamics? Okay. Yeah. No, no. So I'm holding this tutorial session independent of the lectures, but the whole purpose is that I revise the fundamentals for you, the basic questions, and if you have some specific questions, I try to answer them. If I can't, I'll get back to you in the next session, like I just told Ani. So this continuity equation, or what is also known as the Navier-Stokes set of equation, continuity, momentum, and energy, they are the basic governing equations for any fluid. Reynolds transfer theorem is a different thing. Continuity equation is, so see, in mass conservation, you must have seen something like rho AV is constant. Yeah, but is that supposed to be always true? No. Because if you have an unsteady flow, then density can change with time. Right? Okay, I can maybe give you some basics like how to derive this. So you can consider a fluid element. Okay, it has some density. The fluid has density rho, and then you start. You basically see that it changes to rho plus d rho. Okay, so one way to do it is start with a pipe or maybe a fluid which is confined between two plates or something, and I'm just showing you in one dimension, but this can also be done in three dimension. So let us consider this very small length delta x. Okay, what I'm saying is that whatever mass comes in and whatever mass leaves, there has to be a balance, there has to be a mass balance, right? So if I do this mass balance within this infinitesimal control volume, then what I get is the governing continuity equation. And this can change with time, isn't it? Because the fluid flow has some velocity v, and this velocity itself can change with time. So the mass influx and mass outflux can change with time. Do you agree? Huh. Yeah, so in the Reynolds transport theorem, you can actually apply RTT for any quantity, right? So if you apply it for mass, you get the continuity equation. Yeah, if you apply it for momentum, you'll get the momentum conservation equation. Yeah. Yeah, this is for an general, this is the most general continuity equation, where you also take into account the unsteady effects. Right. Yeah. Yeah, that is right. Because see, the del dot will be also. So you have a velocity which is meter per second. So there also there will be a per second. This is kg per meter cube, and this is del dot is again per meter. So that per meter and velocity meter will also get cancelled, and this is again per second. Yeah. So this is correct. Now, what is the question? Okay. 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 Fine. Yeah, so these equations are not explained, is it? Because see, y- before, okay, but a prerequisite of gas dynamics is fluid mechanics and thermodynamics. Okay, so what I thought was we are just going to brush through the basic concepts. So maybe next time I'll do one thing. I'll write down the governing equations for you for a fluid in general. It will be every Saturday, 5 to 7. Yeah. Okay, anything else? Any other specific question? Or anything from what we discussed already today? So I hope this diagram is clear to you. Yeah, PV and TS diagrams. This will come very handy once you start delving into the basic gas dynamics. So you should have all these on your tips. You should know what the different processes look like on these diagrams. Yes. Yeah. High temperature flows. You mean, okay. Yeah. Mm-hmm. I'll have to check the course content. But if you want me to explain from that, you can just tell me the book name and you can tell me the specific section. Okay. That's okay. I'll check it. So the last chapter of the book. Sorry, there was someone else saying something. Yes. So I particularly prefer this book, Zucker and Biblars. It is very good to clear your concepts. And another one is Anderson, the one with modern compressible flows. So Anderson has one on incompressible flows and one on compressible. Okay, so this is very verbose, but Zucker and Biblars is like to the point and very clear. Okay, okay, so I'll look into its last chapter. I have the book. Yeah, yeah, okay, okay, Mhm. Okay. To the point. Yes. So yeah, that is why I recommended Zucker and Biblas. I can even show you the book if you want. It's very good. It's this one. See, if you go for Anderson, the first law of thermodynamics he explains for a long time. Yeah. Yeah, no, but it's very good to clear your concepts. But like these diagrams and all the explanations are pretty good, and the questions at the end, the review questions are also very good. They are very basic, but that clears your concepts. Okay, so you can, and for those who don't know fluid mechanics, you can go through this. So I was planning on covering fluid mechanics in the next session. Yeah, no, okay, I have always referred to the foreign authors. So, okay, I'll show you again. It's Zucker and Biblars. It's called Fundamentals of Gas Dynamics. Compressible flow is all about gas dynamics. Yeah. So all the CD nozzle questions that you all were asking me, all this is a subject called gas dynamics. So here you need the concepts from both fluid mechanics and thermodynamics. Okay, so I'm on recording. I'll if there are no other questions, maybe then we can discuss these things. No other questions? So I'll end the meeting.